Hello Math Studies students, and welcome to your online lesson. Today we'll be talking about the volume of three-dimensional objects, specifically prisms, cylinders, cones, pyramids, and spheres. We will know we are successful when we can efficiently solve volume problems dealing with these three-dimensional objects. So our first question is, what is volume? A lot of times we think of volume as the amount of space that something can hold. And though there's some truth to that, the reality is that volume is actually how much space the thing itself takes up. For example, I can fit stuff into a box, and so it has, an internal space inside of it, or an internal volume, and I could find even the volume of that space inside the box. But something like a block of wood or a stone, which I can't fit anything inside of, still has volume. And if you kind of think of like a tank of water that's filled all the way to the top, and then you were to put a large block of wood or a large stone in there, how much water would pour out once we put the stone into this full tank of water? That water that came out, that represents its volume. It's how much space is now being taken up by that object. So whether it's hollow or whether it's solid, all three-dimensional objects have volume. So, again, the official definition is the amount of three-dimensional space an object occupies. Now, how do we find the volume of a prism or a cylinder? Well, I'm going to draw a quick little prism here, rectangular. And the most common answer that I hear of how to find volume is length times width times height. And there's some truth to that. For this particular prism, that would get the job done. If I think of my length, width, and height, and those are really all interchangeable, I would just multiply them. Length times width times height. But what are we really doing here? Well, if I just took the length times the width, what would that give me? Well, that would give me the area of this object's base. And remember, a prism always has two bases. They're parallel and they are identical in size or congruent. So there would be a base at the top here and there would be a base at the bottom here. And in this case, they're both rectangles, but they could be trapezoids or octagons or anything like that. And so when we take this length times width, or we could call that the base and the height of our base shape of our rectangle, that's essentially finding the area of the base, and then we're multiplying that by the height. And so that actually works for every prism, regardless whether the base is a rectangle or a trapezoid or a triangle or anything like that. We find the area of the base shape, and then we just multiply it by the height of the prism. The same thing also works for cylinders. Cylinders have two bases as well, one at the top that's a circle, one at the bottom that's a circle. And if we first find the area of that base, just one of them, and multiply by the height, that will give us the volume. So let's try this out in some examples. So our first example, we have a prism. The first thing we need to identify is what is the base. And in this case, the base is not on the bottom. Remember, the base of a prism has to be identical on both sides. There have to be exactly two of them, and they have to be parallel. Well, there are several rectangles on here that I can see, like on the right and the left, and they might even be identical, but they are not parallel. Plus, if there's a special shape on a prism, that will assuredly be our base. So our base are these triangles that we have here. So I need to find the area of my base, and then I need to multiply that by the height of the pyramid. Now the confusing thing is, prism. The confusing thing is that we are going to be using the word base to refer both to this triangle base, which is a value of 6, which is just a line segment, and the height of this, as well as the height of the prism itself, and the base of the prism itself, which is a shape. So again, the base of the triangle is just a line segment, but the base of the overall prism is the entire triangle. The height, the triangle has a height, which is 3 centimeters, but the overall prism has a height as well, which is 10 centimeters. So how do we find the area of a triangle? It's 1/2 base times height. And then we're going to multiply that by the height of the prism. Well, I don't want to really put an h here because I'm already using an h previously and they don't have the same height. So I don't know if we want to use like a different variable, like a little p to represent prism height, or h sub 1 and h sub 2 for the two different heights that we have, or if we just plug the values in. But I just want you to be careful to not confuse those h's together or those heights together. So we have 1/2. The base of our triangle, again, is 6. The height of our triangle is 3. And then the height of our prism is 10. Now we can multiply all these together. When we multiply 1/2 times 6, well, 1/2 of 6 is 3. And then 3 times that other 3 gives us 9. And 9 times the 10 gives us 90. Now, what units are we going to have here? Well, we started with centimeters. Volume is measured in cubic units. What do we mean by that? Well, cubic units, if we have a little cube, which is essentially a prism that is the same dimensions in all sides, like a little square box, and we're basically saying how many of those boxes have the same space as what would go into this prism or tent-shaped prism that we have here. That's what we're measuring. And so we use not centimeters squared, but centimeters cubed to represent cubic units, or cubic centimeters in this case. For our second example, we have another prism. Once again, we have to find the area of our base. Our base will always be the special shape, if there is one present, and that is this trapezoid out front here. So we need to do the area of our base times the height of our prism. How do we find the area of our base? Well, it's a trapezoid, so that's going to be 1/2 times the sum of our bases. Or another way to say that is we average our bases, add them together and divide by 2 or multiply by 1/2, and then times the height of the trapezoid, not the height of the prism. So I'm just focusing on this base of the prism, this flat surface here that is a trapezoid. And so our two bases are the parts that are always parallel. So we have this 8 centimeters and these 14 centimeters. So I can do 1/2 times 8 plus 14. And then we have to have the height of our trapezoid, not the prism yet. And so our trapezoid has the height of 4, and that would be the perpendicular distance between the two bases, the 8 and the 14. And I can go ahead and simplify this, but we also are going to have to eventually multiply this by the height of the actual prism. So right from the get-go, I can go ahead and multiply all of this times the 10, which is the height of my prism. Or again here, multiply all this times the 10. And now I can throw that all in my calculator. Where I used brackets, you could just use parentheses in place of that. I'm just showing we had, again, this whole region here was the area of our base, which was a two-dimensional shape, in this case a trapezoid. And then here we had the height of the prism. All right, I'm going to throw that in the calculator, and I end up with 440, which would once again be centimeters cubed, or cubic centimeters. So to recap, we took the area of our base shape of our prism and then multiplied it by the height of the prism. Now we're going to find the volume of a cylinder. So cylinder, remember, it has circles for its bases, and then it essentially has a rectangle that's wrapped around it, sort of like a tube or a pipe. We see them in the real world both standing vertically like a smokestack, but also going horizontally like this one, which we might have for some plumbing or a sewer system or something along those lines. Once again, the approach is the same. We're going to do the area of the base, and in our case, our base is a circle, so pi r squared, and we see those two identical parallel bases here on the left and the right, so they don't always have to be at the top and the bottom. And then we're going to multiply that by the overall height of the prism. And thankfully, circles don't involve an h, so I can write out the formula just straightforward like this. So the area of my base right here times the height of my prism right there. Only two variables to work with. We have pi r. R is radius. We're actually given the radius here, not diameter, so I can have pi 6 squared times the height, which is going to be 18 of my prism, so 18. And then pi r squared, that would be 36 pi, and I'm going to multiply that by 18, and I get 648 pi. Units, we're dealing with inches this time, still going to be cubic. And so there would be 648 times pi, and remember pi is a number a little bigger than 3, cubic inches. I'm leaving it as pi so it's exact. Of course, we could round it to 3 significant figures, but it'd be an extra step and an extra chance to possibly make a mistake. But you'll notice we're still dealing with the area of our base here. And whatever formula that is, we've now looked at rectangles and looked at triangles and trapezoids, and then here circles as the area of our base, but then always times the height of our actual prism or cylinder. Now we're moving on to the pyramids and cones, as well as the spheres. Let's start with pyramids and cones. You'll notice here for both pyramids and cones, they follow the same basic template that we used for prisms and cylinders. You start by finding the area of the base. A prism and cone, they only have one base, but they do still have bases. And again, that will usually be the special shape. And then we multiply by the height, and we're talking about the height of the prism. So it must be perpendicular or a right angle with the actual base, and then it would go to the peak or the apex or vertex of these little shapes here, the pointy part. But there's an extra step, because obviously since these sides here on the pyramids and cones are like angling in together, they wouldn't have as much area as a typical cylinder or prism. We end up multiplying it by the scalar or coefficient of 1/3. And that's true for both prisms and bases. So anytime we're dealing with something that ends with a point, like a prism, like a pyramid or a cone, we just multiply our normal volume formula, area base times height, but times that extra 1/3. Now spheres are even different still. We start off with this pi r cubed. Well, that reminds me of pi r squared that we'd use for area, but we are dealing with volume. We do have labels that are cubed, so we multiply by another r. That kind of makes sense there. But then this 4/3, we just kind of have to remember it. Something I would point out, when we were finding surface area, we did multiply our pi r squared times 4. And so that's got some similarities. And then you'll notice that both of these have a 3 in the denominator, both for pyramids and cones as well as spheres. So that's my best attempt to sort of make some connection between what we already know and these new formulas here. Let's do 2 more examples. So let's start with the pyramid. And again, anything that works for the pyramid, we do the exact same approach for a cone. And what is that approach? We find the area of our base. In this case, our base is a square. How do you find the area of a square? Base times height, or one of its sides squared. So we'd have 16 times itself. So you could write 16 squared, or 16 times 16. And that would be the area of our base. Then we're going to take that, which is 256, but we also need to multiply by the height of our prism, or in this case pyramid, I'm sorry. And that is going to be, yes, so we have 2 options here. We have this 17. Now we use that 17 for surface area because it was the actual perpendicular height of the triangle. So when we were trying to find this triangle area for surface area, we needed that 17. However, that is slanting. We called it the slant height. It is not the actual height of the pyramid. How do we know? Because here the base of our pyramid has a right angle here, and it goes straight up to our apex, this vertex right here, this point up top. And so 15 would be our actual pyramid height. And we can multiply that by our 16 and our 16. But we also have to remember, since it's not a prism or cylinder and it ends in this apex or point, that we also have to multiply the scalar of 1/3. So we'll end up with 1/3 times the area of our base, 16 times 16, times the height of our pyramid, which is 15. And I'll throw that in the calculator. And we end up with 1,280 inches cubed, because we're dealing with volume. What are we going to forget most likely? Probably this 1/3. It's still the area of the base times the height, but we just have to remember to do that 1/3. How do we know to do the 1/3? Anytime it ends in a point, like on a pyramid or a cone. Our last example is going to be a sphere. I'm going to start by writing down the volume for the sphere. This is one where it doesn't matter what kind of sphere you have, there's just one formula. You don't have to worry about changing anything up. So it's 4/3 pi r cubed because we're dealing with volume here. So I can just plug this in. We have 4/3 pi, and then our r is 2.8. So we have 2.8 quantity cubed. And I'm going to throw that into a calculator. And I end up with this decimal 29.2693 repeating, which is not particularly friendly. I could always hit math, enter, enter, and on my calculator end up with this fraction 10,976 over 375. So in this case, I'm just going to multiply by pi and round because my answer is not particularly easy to write even when I'm leaving it exact. So my volume is going to be equal to 40,445.64 something something something, going on and on and on. Since I'm rounding, I need to round to 3 significant figures. So I would have 4, 0. 4 would be my third, and a 4 comes after it, so I'm rounding down. And then I need to fill in placeholders for everything else before the decimal point. So I'd have 40,400 centimeters cubed as my volume answer. All right, so those are some examples looking at volume. Again, area of base times height, unless it ends in a point where we multiply by 1/3, and the sphere is 4/3 pi r cubed. Until next time.